First thing we're going to look at, though, got a demo for you. So at the top of your page, so first thing we're doing is you label this phase change demo. And you're going to leave some room. So what we are going to do here is we are going to measure here, right here, we are going to measure to see if when we boil the liquid water and we have steam above it, are they both going to hold off at the same temperature? Is the steam going to get hotter? All right? So notice they're about, so the red is the liquid, it's about 23 and a half, and the bottom a little under 23. So they're about a degree apart. That has to do with the thermometer. So they're starting about a degree apart. And we're going to run this. It's going to take a while. So make a hypothesis. What do you think is going to happen to the temperatures when we reach the boiling point, when we reach that 100-degree boiling point? What do you think is going to happen to our temperatures there? Are they going to hold at the same temperature? Is the water going to get hotter? Is the steam going to get hotter? And so on. So we're going to start that running like that, and we'll come back to it so it's on the hot plate. So then leave some room for a conclusion. Yes, sir?
Is it possible that iron can you purify water with mercury?
Well, electrolysis, you run electric current through water, it'll break it into oxygen and hydrogen. You can then re-burn that, and when you burn hydrogen and oxygen together, you get water. So you can purify water that way. That's possible. Kind of a slow, hard way of doing it. There's a lot easier ways to do that. One of the ways is you boil it, capture the steam, and then condense the steam. All the impurities left behind. How we make water on the ship? Well, before we had these things, reverse osmosis. Now they have like this magic membrane. You force water through it, seawater through it, and water goes through the membrane, but salt stays behind. You do it that way. But we used to use distilling, and you would boil the water, and the water would condense back out, and you'd have pure water. And we can see a little bit. So you notice the gas, the air above it isn't really doing anything yet. But notice our water is going up in temperature already on that. So let's talk about other stuff. So last time we talked about phase change and stuff like that. Today we are going to talk, and we talked about that thermodynamic. We ended with sign convention, first law. We're going to talk about some thermodynamic processes. Now remember the first law, the general statement of the first law, change in internal energy equals heat plus work. Okay, that's what we did last time. That's the first law of thermodynamics, was conservation of energy. There are lots of thermodynamic processes. The book only talks about one thermodynamic process, and that's adiabatic. We'll talk about a couple others later on. But in the adiabatic process, now the adiabatic process is very important to weather issues, and some things has to do with combustion and things like that, internal combustion engines. And what happens is you take these thermodynamic processes and you put these thermodynamic processes together for thermodynamic cycles. And thermodynamic cycles are what describe basically how certain types of engines work. We're going to look at the Otto cycle, O-T-T-O. This is a gasoline engine. There's diesel cycles, Brayton cycles, Rankine cycles, things like that. But in adiabatic processes, no heat is added or lost. Only work affects the change in internal energy. So Q here equals 0. So delta U equals work. Delta U equals work. When we say work, what we're looking at here is a change in volume. Volume gets greater, work is being done. That means the internal energy is going to go down. Volume gets smaller, work is going to be done on it, and the internal energy is going to go up. And one more time. So one of these atmospheric processes. Now this is one of the reasons why we have what's called a rain-shadowed desert in the basin and range area of the United States. That's the area between the Rockies and the Sierra Nevada and Cascade Mountains. If you are west of the Rockies, or east of the Sierras and Cascades, you find very hot and dry. It's like even Washington. We consider Washington wet and cold and all that. Have anybody ever been to Spokane? It's eastern Washington. Spokane, hot and dry. Okay, not like Reno, which is a lot hotter and drier. Reno's farther south. But compared to western Washington, in fact, even western Washington, you get up on the Olympic Peninsula, I mean, it's a rainforest. The very western coast of Washington is a rainforest. Rainforests aren't only tropical. The rainforests do occur, it's called a temperate rainforest. It has to do with how much rain they get every year on that. So, but lots of water and cold, things like that. In eastern Washington, hot and dry on that. And this is because of this process. So what happens, now remember what we're looking at here, we have the Sierra Nevada mountains. Reno. Sacramento. So remember that air we talked about, that air that comes along across Valley Forum there, it's picking up, it's fairly moist air coming from the coast. It's picking up energy though, right, off the thing. Some of it goes back and forms a wind. Well, some of it keeps on going to the Sierras. And some of it's that westerly wind back to the Sierras. And what happens, it hits Sierras, and the Sierra Nevada mountains push it upward. Right? It slopes up. It's kind of like you're like that. Well, as it goes up, you have this fairly high pressure warm air. It's going up, and as it goes up in altitude, let's think it's like a balloon. As the balloon goes up in the sky, what happens to it? It starts to do what? It starts to expand because the pressure inside is greater. That's what happens here. That pressure expands. Remember what we said, that means work's being done. Work's being done to push it farther out. Internal energy goes down, that air mass gets cooler. Eventually, that cooling air, because our humidity gets below the dew point and things like that, relative humidity, well, that water starts to condense out in the air, forms clouds, and eventually starts to rain out. Why, remember, our side of the Sierra Nevadas is nice and what? Keyword. Green. The Reno side of Sierra Nevada mountains, not so much, right? Green on our side, not so green on the other side. That's because once it gets to the top here, now we have cold, less moist air, but okay, sort of moist. There's cold air, but cold air does what? Cold air is dense, and it starts to do what? Go down. Now, the only reason it's gone up all this far is a lot of it is because the mountain is forced it to go up. Now it starts to sink again. But now it has less pressure. It has that less pressure, the air around it starts to push on it, starts to compress it. As it compresses, it warms it up. What's happening to the relative humidity of this air? Going up or going down? Getting warmer. We haven't added any more moisture, but it's getting warmer. Relative humidity is going to go down. Remember, now the air can hold more air, more water. So we get this very low humidity air coming down the mountain, which means does it want to give up any moisture? No, in fact, it's probably any moisture it encounters is going to get what? Sucked up, right? It's going to evaporate it, it's going to suck it up. So you end up with these warm winds that come off into Reno that's drying everything. We call those Chinook winds, where they come off the top. Same thing happens on the Rockies. It goes up the Rockies, the eastern side of the Rockies, all nice and green and everything's going. The eastern side of the western side of the Rockies, Utah, places like that, not so green. Okay, so it forms that desert. Base of the range area is what's called a rain shadow desert. Okay, you can notice the rain on either side gets blocked. We also see that as the air rises in these skies. We go up in the sky in weather mass, you get adiabatic heating and cooling. In general, every kilometer you go up, you're going to see a cooling because as the air rises and spans, it's going to lose about 10 degrees every kilometer we go up, which is about every 3,200 feet, 3,500 feet or so up in the sky. It's about 10 degrees of temperature on that. You might say, why is Sierra Nevada mountains, why does it get like that? Seems like when you're at the top, that's about 6,000, 8,000. That's like up here, it's minus 5 degrees. Remember, this is like an open air. If you're on the mountain, you also have the heating of the ground and things like that. There's other effects. So, stuff like that. So because you're still here, near this warm air is coming in still up the mountain. It doesn't appear with that air up here. So let's do this process another way. So we have a 4-stroke engine. I know there's 5 pictures. It's kind of confusing. You probably read that 4-stroke engine, but they have 5 pictures. Four-stroke engine. Now I know this is a gasoline engine. I wouldn't even have to be told it's a gasoline engine. I just have to look at the picture. I know it's a gasoline engine. Anybody know what component here tells me it's a gasoline engine? Spark plug. Yeah, spark plug tells us gasoline engines have spark plugs. Diesel engines do not. Diesel engines do not have spark plugs because diesel engines have a much higher compression in here. And remember, what we said, what happens to the internal energy when we compress? Makes things hotter, and it causes the diesel air mixture to explode on its own. That's why when if you ever turn off your car and it keeps running, usually because your valves are leaking, usually oil gets in the cylinder, we call that dieseling. It keeps running all by itself without the spark plug going on that. Always lived when I was a midshipman in 3rd class. See, send you the police and list them in. They'll go, well, go give me a spark plug for that diesel. I was on a diesel powered ship for my first cruise, and they would send us to get spark plugs. They get mad at me because they find me in my rack. I can go take a nap. I said, well, the only place I'm going to find a spark plug, a diesel engine spark plug, is in my dreams. So I went and took a nap. A lot of people they're used to other people new seamen don't do that. New firemen, they kind of get confused on that. But notice compression and ignition are the same step. Now, at 1, 2, 3, 4, how many times is work actually being done to your car? How many of these 4 steps, where do you actually get something that makes your car go forward? Yeah, power stroke's the only time. So in other words, only 1 out of 4 times you're getting power, which means really, what is the minimum number of cylinders you need for your engine? 4. Those minimum amount of cylinders you find in most cars is 4. And yeah, they make 3-cylinder engines, things like that. They don't run that well. And the more cylinders you have, honestly, faster the smoother. Because remember, it's like bang, 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 bang. You get 1/4 of the time you're getting explosions. That is kind of rough. V8 engine, it's an 8 every 1/8 of a time. Is that going to be smoother? Basically getting a push every 1/8 of a time. What if I had 12 cylinders or 16 cylinders? By the way, cars with 16 cylinders cost about what a house does. But they're very smooth. Their engines are very, very quiet because So, cars with 16 cylinders, they have things like Rolls Royce, Bentleys, Maseratis, things like that. Most of us have to be happy with 4, 6, or 8. 4 gives you more power, but they're also a lot smoother. If you really listen to an 8-cylinder engine, and a big 8-cylinder engine compared to a 4-cylinder engine, it's a lot quieter on that. Now, if we look at this, you see we have this power. What we're looking at is a pressure volume diagram here on the various parts. Now, this is an Otto cycle. A cycle is several different parts put together. Notice right here in the intake phase, we are intaking. Notice our volume is changing, but pressure isn't. We would say this is an isobaric step, isobaric process. Notice we're taking air in from the atmosphere. Air is the working fluid of our engine, not gasoline. Most of what's in the cylinder is air, with little teeny tiny bit of gasoline. We'll get to the gasoline in a minute, or diesel, or anything else. Working fluid for an internal combustion engine, whether it's this type, piston-driven, jet engines, things like that, is air. Air is the working fluid, and they're called, in their external cycle engines, because they bring in from the outside and they expel to the outside, as opposed to a, internal type cycles like a steam engine. You're always recycling the water. On like a steamship or a power plant, steam engines don't. They draw in water from the outside and they expel it to the outside at the end. on that. So we have our intake. Now after our intake, next part is compression. Now right here is adiabatic. Notice we are decreasing the volume, which causes a pressure increase, but are we adding any heat? So in this section right here, this is adiabatic compression. Adiabatic compression. We get to here. Now we'll jump up here. Right here is where we ignite the fuel. Now notice, from here to here, did we do anything to the volume? No, this is what we might call an isovolumetric or isochoric step. We're increasing pressure, but we're not increasing the amount of volume. We didn't do anything to the volume, but we increased pressure. In other words, we added heat. We added a lot of heat here, because this is where the spark plug goes off and all that gasoline ignites. The purpose of the gasoline is basically to raise this pressure. So that's it, boom, it raises the pressure. Then we're on our power stroke. That gas expands. Work is done by the gas. Again, this is adiabatic expansion. So this fluid in there is cooling. The energy, the internal energy is being converted into work. A little bit here at the end, it goes back, because when we open the valve here, it's going to go back to atmospheric pressure, and we're back to that isobaric pressure. Yes, sir. Well, lots of reasons for a cylinder failure. Could be, you have rings here. You basically have seals here. Sometimes your rings blow through. So you no longer have a seal. If you have no seal here, that's what things called rings. It's like a seal. There's several of them depending on the piston. And they basically run up against the cylinder wall, which is why you have oil. And they prevent the gases from leaking around. So you could have a cylinder fail that way. You could throw a piston rod. In other words, this thing gets banged down, this piston rod breaks off and out the bottom. Valves stick, valves disintegrate, you could blow the head off. So piston failure is a whole, there's tons of things that could come under the heading of piston failure. It could fail out the bottom, which is bad. It can fail at the top, which is bad. Basically, there's nothing good about piston failure. Because basically, and the thing is, you can't do one. Like if you replace like the heads and things like that, a lot of times, if you replace the head part, the bottom's going to blow off very shortly afterwards. Basically, when one part goes, you have to rebuild the whole engine. The way that goes. Been there, done that. Had a head gasket glue on it, and basically they replaced the middle part of the engine. So, some of these other processes. We're not going to worry about that one. Not that part. Isothermal. Now we're going to go through each part. Now adiabatic, remember, heat was zero. Internal energy has to do with work. On an isothermal, remember, temperature has to do with internal energy. This means that our change in internal energy is zero. There is no change in internal energy. If I do work on the system, it immediately goes out as heat. If I add heat to the system, it immediately goes out as work. Goes through. So I can say now that Q equals negative W. Because they're going in opposite directions. Any more time? Last one is isovolumetric. Now remember, there's lots of these processes. I'm only going to deal with these, talk about these three. Isovolumetric, well, this means volume is constant, which means work is zero. Any change in internal energy is equal to the heat added or removed. That was that little spike up of our Otto cycle, and so on. All right, we're going to take a look at our experiment, our little demo here. Anybody need more time on this? We good? Good. Well, let's take a look at our demo. So here we are. Now notice the nice linear, kind of looks like those graphs, right? As we're going up from our boiling point. This is the water. This is the liquid. This is the air above it now. So notice it's going up. Now, why is it's heating up now? We have here, now we have a little bit what looks like boiling, but remember, they're kind of heating up. But if I touched up here, now you saw me lift it up, would I want to grab this here right now? No, it's very hot. Notice there is water, liquid water on the inside. Where did that come from? Well, remember, as I increase the temperature here, and we're almost at the boiling, that's why it's going like this. As we increase the temperature, we increase the evaporation rate, right? And when that water evaporates, and that's where the heat for the air is coming from, is from that evaporation. But when it touches the glass, it condenses, and that energy goes to the glass, makes it very hot. Now you can see, notice we came to the right point. See, we're boiling. So notice we're at a little over 100. We might go a little above because we're containing pressure, right? I'm only have this one little hole here, so I'm putting pressure on there. So it goes up a little higher. But notice how this thing has really started speeding up. It came up higher because notice once I started boiling, am I putting a lot more energy up there? Yes, I am. But notice they're both starting to level off. It's also starting to clear up in here. And you can hear this stuff coming out. Here, up here is steam. And every once in a while you can see a little wisp up here. There, that's not steam, that's liquid water. And you can see it, it's liquid water, then it disperses. So there's not enough there to see it anymore. Notice our boiling temperature is a little bit over 100. It's because I put pressure. It's kind of how a pressure cooker works, by trapping in. I mean, if I didn't have a hole there, would this get even higher? Eventually it would pop it off. Remember, if it's a pressure cooker, you got to lock the top on. But this is also how a reactor works. A nuclear reactor, this is how nuclear reactors, they don't want it to turn to steam. They want it to stay liquid water. What happens is it starts putting pressure on the liquid, so it gets very hot, which is called a little steam bubble. Most of the time when you hear there's been an explosion in a reactor, the explosion is that steam bubble. Basically, something fails and that steam bubble comes out of the reactor chamber. I mean, reactor doesn't explode like a nuclear weapon. Usually it's a steam explosion. Steam gets out. It's like a cork in a bottle. But notice what's happening. They're both leveling off. They're going to get to a point. So basically, do you think that these are going to change before all one or the other's gone? Yeah, they're not going to go anywhere. They're going to just level off. And notice if I take this, now I want you to watch this carefully. Notice it's boiling, nice and boiling. When I take this off the hot plate, it's boiling. Notice how quickly it stopped boiling. It's a cooling process. And notice there's not as much energy going up in the air. What's happening to the air temperature? Going down. Why isn't the water going down that quickly? Well, it's not still up, but unless we have to think about water, liquid water, how fast does it cool off? Very, very slowly. Yeah, it takes a long time on that. We may have time to look at that. But notice our air temperature, it comes down rather rapidly. Mainly because like air from the outside is getting into the hole and things like that. Right at conclusion about what you saw in that, about that the temperature really does stay at the same level when you hit that phase change point. They will stay at the same level. That is the problem in a steam boiler. You have to get rid of all that water before you can add more energy, what we call superheat. You got to take away all that liquid water out of it to get to that point. right. Now, give me another 30 seconds to write that up. Which leads us to the second law of thermodynamics. And the first law is kind of like your break-even law. Whatever you put in, you can get out. Second law has a couple of parts. Second law deals with a couple of things. Now, the easiest way to say the second law, heat will never of itself flow from a cold object to a hot object. You can force it, but it will never of itself go from colder to hotter. No time will you ever see something get colder while something else gets hotter. To do that takes more energy. We call that a heat pump. Basically like your air conditioner. Your air conditioner basically takes hot air out of your house and expels it outside to a hotter environment. From a colder to a hotter environment. No, any more time? I have a little video to bring home my points.
I'm worried about the kids, homie. Lisa's becoming very obsessive. This morning, I caught her trying to dissect her own raincoat.
I know. The perpetual motion machine she made today is a joke. It just keeps going faster and faster.
And Bart isn't doing very well either. He needs boundaries and structure. There's something about flying a kite at night that's so unwholesome.
Hello, Mother dear.
Oh, that's it. We have to get them back to school.
I'm with you, Marge. Lisa, get in here. In this house, we obey the laws of thermodynamics.
So why did Lisa's machine disobey the laws of thermodynamics? Well, he said it. What does it do? It's going faster and faster and faster. In other words, it's creating more energy. You're getting more energy out than you put in. So on that. So you can't do that. You can't do that. Now, the second law has a number of corollaries. One of them applies to heat engines. Heat engines are like our car engines, steam engines. And a heat engine is a device that changes internal energy to work. Changes that internal energy to work. And there must be a temperature difference between the heat reservoir, Q sub H at a high temperature, and the heat sink, Q sub C at a low temperature. Now, it's easier to see this with steam engines because there is a different heat reservoir and heat sink. Less able to see it like an internal combustion engine like your car. The heat reservoir is that part when the gasoline ignites. That's the heat reservoir because you have a high temperature, high energy, lots of heat at that, and it expands, goes in, that gasoline goes into the fluid, expands, does the work. The atmosphere is the heat sink. But notice, there has to be a high temperature area and there has to be a low temperature area. Which means, are you converting all of the energy to work? Yes or no? No, you're not. Anyone need more time? More succinctly, it's like this. The second law, this is how this corollary for the second law works. When work is done by a heat engine running between two temperatures, T hot and T cold, only some of the input heat, Q sub H at T hot, can be converted to work. And the rest is expelled as waste heat, Q sub C at heat cold. Now you might say, well, that seems to violate the first law. Now the first law says I can break even. In other words, QH can be converted to work. First law says I can do that. But the second law says, no, you can't. In order for a heat engine, that's your gasoline engine, diesel engines, jet engines, steam engines, all those kind of engines. In order for them to work, there must be a high temperature and a low temperature. Some of the energy must go to waste heat. You cannot make it go all the work. It doesn't work. Just, in other words, it would violate the second law of thermodynamics on that. Has to have that. Now the idea is to minimize those two as much as possible, but you cannot totally eliminate it. But it does still meet first law. You might say, well, that sounds like I'm violating the first law of conservation of energy. Well, you're not really. Q sub H, the energy I put into my heat engine, equals the work that comes out plus the waste heat. Notice what I put in is what comes out. Now, not all. The idea, what this is saying, is not all of it's going to come out as useful work. Not all of it's going to be making your wheels go around. Not all of it's going to make that propeller shaft go around. Not all of it's going to make that generator go around. Some of it comes out as waste heat. And although we call it waste heat, that doesn't mean it's not usable, by the way. And we usually express this in terms of power. Rather than express it in terms of energy, we actually do it in terms of power. The power we put in, the number of watts we put in, equals the watts we get out, watts waste heat. Because we want to know over time, in other words, our generating plants, we only generate plants, how many kilowatts and things like that. Now, waste heat, is it not usable? Well, no. Like on our destroyer, we had a waste heat boiler. We had gas turbine engines that ran for main engines. Basically, the same engine you would find on a C5 is what we used to drive the ship forward. So it's the propeller shafts. We had smaller jet engines for our generators. They ran at constant speed. Basically, these were the same engines that you find on a C-130 Hercules. It's like a propeller-driven cargo plane. They have turboprop engines, so it's a propeller, but the propeller is spun by a jet engine. Okay, so the little jet engines, but the exhaust from that goes through the tubes of the boiler. So some of the exhaust energy is used to make steam, and we use that steam for cooking, and we use the steam for heating the ship and for making water. Alex asked you earlier about making water. That's where the steam comes from to boil the water, the seawater that we use to make our fresh water and more water for the boiler and things like that. So we do that. In a commercial power plant or a big steam plant, we would use some of that waste heat when it is actually going to go through the feed water. In other words, before the water goes into the boiler, there's actually heat exchangers, so the water coming out goes through this feed water and heats it. So you're taking some of the energy from that water that just came out of the system and using it to heat the water just before it goes back in the boiler. So you get some energy exchange there. So there's a number of ways these things do. Now, can you use all of it? No, there's still ways on that. Anybody need more time? So we got to have our diagram here. Well, this diagram, very important diagram, good diagram to have on the thing. It should be in your notes on this. So we have our high temperature area, T sub H, and we put in energy. And there we have our heat engine. And our heat engine, this could be a jet engine, this could be a steam engine, the pistons of a steam engine. This could be the turbines of a steam engine. This could be the pistons in your car, diesel engine, gasoline engine, so on. And some of that's going to come out as work. But some of it's also going to come out as Q sub C in our heat sink, T sub C on that. More time. And this is, and the whole point here is the greater the difference I can make this temperature, the more energy I can extract to be making work. In fact, on the Missouri, So we think our steam temperature was about 700 degrees Fahrenheit going in. It's under pressure, so 700 degrees. But the condenser, the waste heat, the heat sink, was kept at a vacuum, so it lowered the boiling temperature. So the water coming out of the turbines is only about 100 degrees Fahrenheit. Well below what you would think of as the boiling point of water. So they were able to extract more energy out of it. Steam systems have very, very energetic systems. Steam locomotives, when they replace steam locomotives with diesels, it takes several diesels to do the job of what one steam locomotive used to do. They're cheaper to maintain and cheaper to run. Steam destroyers, the old World War II steam destroyers, much faster than our modern destroyers in anybody's Navy. You know, those old steam destroyers would go over 40 miles an hour. Modern steam destroyers, you know, they might get, if they're lucky, you might hit 32, 33 miles per hour, 35 miles per hour, things like that. Aircraft carriers, which are steam-powered ships, are basically only limited in speed by what the strength of their shafts. You know, you don't know how fast. In fact, even on Missouri, we never went the top speed of the ship. And only 3 people knew what the top speed of the ship was supposed to be. And that was the CEO, the XO, and the chief engineer. Which I was none of those 3. Cheaper. You know, aircraft carriers need speed for making wind over the deck. Gas turbines are easier to maintain, they use less fuel. Missouri, I mean, we could go fast with a lot of things, but we burned about 100,000 gallons of fuel a day. I mean, we held like 2.2 million gallons of fuel. And every 3 days, when we were on station in the Arabian Sea, when we were outside the Straits of Hormuz covering tanker convoys, about every 3rd day we take off 300,000 gallons of fuel. You know, that was about an hour of unwrapped time. It would take us about an hour to do that. So we'd have to sail alongside of the fuel into the oiler out for an hour. 2 stations, each one gets about 150,000 gallons an hour. Suppose about this big around. Distillate fuel doesn't burn as hot as bunker fuel. The old fuel they used during World War II, you see pictures of ships get torpedoes all black and oily. It's really thick bunker oil. It burned a lot hotter. They got like better mileage out of it. But it doesn't work more proven on that. Anyone need more time? So a steam plant. So here's our steam plant. This could be in a ship. It could be in a power plant. Being the turbine here on board a ship, you hook the turbine to a propeller, to reduction gears to a shaft. In a power plant, you hook it to a generator. And basically all steam plants work the same way. The only difference between different steam plants is how do I boil the water? You know, I can boil the water using uranium. I can boil the water using natural gas. I can use oil. I can use coal. I can use mirrors, solar power. There's solar power plants. There's steam plants. They aim all those stuff at the boiler. The mirrors aim the sunlight at the boiler. I can use steam from the ground. But still, we're making steam. Doesn't matter how I get it. Once I get it, I have steam. And that steam is high pressure, so I have my Q. Here's my QH going into my turbine. High pressure steam. Coming out is low pressure steam. This is my QC. Right, coming out is work. Turbine, that's the work on that. You know, and now this is a closed cycle. Notice the water gets pumped back to the boiler and is used over and over again. Whereas other things. Now, I do have a picture of an open cycle steam plant. This is the largest operating locomotive currently in the world. Mind you, those are standard boxcars, railroad cars behind it. There's the engineer right there. These are the people standing. This is a 4.6. This is Union Pacific's 4664 Challenger mallet type locomotive, which means it had 2 sets of drive wheels. So you have 4 in the front. You have a set of 6 drive wheels with a piston, then another set of 6 drive wheels with a piston, and then 4 smaller wheels that support the back end. This was not the largest locomotive ever built. Built this size building, it would go about 70 miles an hour. Union Pacific was called a 4884. So instead of see how you have 3 wheels, they would have 4 wheels on each side, 4 and 4. Called the big boy, that was the largest. Southern Pacific. How many of you have ever been to the Railroad Museum in Sacramento? You know the big giant engine that's in the middle? That also is a 4884. Only that one is a cab forward. Southern Pacific flipped their engines around. Now most of those tank cars, those are water. It's not fuel, it's water. On that. Most of what you saw there, it's going slow through the arch, but Southern Pacific, if you get there, if you ever go to the Railroad Museum, how big were the wheels? You guys remember how big the wheels are? Real big? In other words, if I was standing in front of them, would I be taller than the wheels? No. The wheels on that thing, they're bigger than I am. Drive wheels. Those cab forwards were meant to haul things over the Sierras. Even then, it might take a couple of them to get over the mountains. Now the water, the reason there's a lot of little towns, you ever notice like you go to Central Valley, you go places, all the towns seem to be the same distance apart? You go to Central Valley, all these little towns, especially if you're on 99, all the towns are about 30 miles apart. You ever notice that? Because that's how far the train could go without needing water. The train would go about 30 miles and they had to put more water in it. When they originally built the railroad. That's why all those little towns are there. They were basically a station with a water tank. They put water. Fuel they could carry. The fuel, didn't use up fuel. Because Southern Pacific, they used oil. But like there was one stretch in the Sierras, like a 9-mile stretch. The tender, if you ever go there, the tender holds like 22,000 gallons of water. In one 9-mile stretch, they would start with 10 to 2,000 gallons of water, and by the time they got to the other end of that 9 miles, there was about 700 gallons of water left in the tank. And why they used all that water? Because it took so much effort. The more water they're using has to do with how much they are working the engine. The more steam they're doing. But it's not a closed cycle, so the steam gets expelled. Unlike this steam engine, where they recycle it on a steam locomotive, once they use it, it goes out. It looks more like something like this. This is kind of how a steam locomotive. Now this is a factory. This would be a setup for a factory. You might recall we saw that video about the wheel. They talked about the water wheel, right? The water wheel ran the factory. But what if there's no water? You have a problem. Back east where the rivers run pretty constant, that's okay. But in the West Coast, does that work very well? No. In fact, if you go up, there's the Bale Grist Mill. It's up north of St. Helena. It's like one of the largest water wheels around. They still work it. They bring the water in. But it's a grist mill, which means they were grinding flour. Well, like during the summer, they can only grind like a couple hours a day. Because they have a pond, and they let the water fill up in the pond, and then they let the water out. And they run the mill for like a couple hours, but it drained the pond, and so they'd have to stop. And it took another day for it to fill out with more water. In the winter it wasn't a problem, but in the summer there's not a lot of water. This solved that problem. I'm not at the whim of water anymore. Now I can control this. So the steam comes on the other side, and it's going to be connected to a flywheel. Now on locomotives, this part's the drive wheel. Right, that steam piston works the same way. It goes back and forth, back and forth, back and forth. This is what's running it on that. And then we hook up to all these wheels. It's running all these little belts and things, running to all these little machines on that. And we get something that looks like that. And we have this whole process going on in that. And that's it. So write your summaries. Remember, storybooks. Write your storybooks.